bit proud also of being here. And I'd like just briefly to drop some introductory words and then hand over to Marco, because it's his PhD project that he is implementing at Leibniz University here in Germany. And he can very good and much better than me show you what our ideas of fostering scientific reasoning competencies are. And Marco worked in an introductory lab course, and our idea was to design and implement and also to evaluate a learning sequence, including several experiments based on research evidence, and to implement this in a Gen Chem lab. Very briefly, we can also very good link to what Gwen Laurie said in her presentation. Our idea was also to redesign or to focus lab education differently, and moving from like cookbook like lab education to a more inquiry oriented way of working in the lab. And basically what Marco did is he adapted experimenters in the field of kinetics from the left-hand side to the right-hand side. So confronting the students with the problem of designing and carrying out an own investigation in the lab. And our idea was to foster scientific reasoning competence. So the project of Marco is basically located in the competency framework, or the idea of competencies that I'd like to briefly explain now. So let me briefly also say that scientific reasoning is one of the science education grant goals, I would say, implemented in so many standards around the world. And it's also one reason that we focus on this construct. And you may also know that there are tons of literature, tons of articles about what scientific reasoning is, what skills and knowledge it encompasses. And let me also just briefly say that it comprises a wide range of skills, like identifying problems, developing research questions and hypotheses, carrying out experiments in order to generate data, evaluating claims also based on data, and also judging and evaluating scientific investigations. And when you think of scientific reasoning as a part of competencies, you have to keep in mind that competencies are dispositions that are acquired to successfully cope with certain situations. And I think there are 5 key points that you have to keep in mind when Marco is continuing to talk about his implementation and evaluation of what we did in the lab. So competencies are domain specific. So they are specific for chemistry or even the field of kinetics where Marco worked in. They comprise cognitive components as well as affective components, or social and ethical components also. They are learnable. It's not just intelligence. That's something that you have very often to tell to educational psychologists. Scientific reasoning competencies is not just intelligence. They are dispositions that enables individuals to perform successfully, and they comprise the idea of transfer. So the idea of competencies and developing competencies is to develop skills in a certain problem-based situation, and then being able to transfer it to a different problem that is quite similar. So you become competent in dealing with problems of coming from the same family of problems. Okay, so Marco published based on some quantitative data already in the International Journal of Science Education, a framework where we also can locate, and we say, okay, scientific reasoning can be carried out using different inquiry methods, such as observing, experimenting, and using models. And Marcus will now show you how he implemented the inquiry methods, of course, of experimenting into the lab. So Marco, enjoy. And I think we hand over now the presentation, right? I will finish my presentation.
Yes, thank you very much.
Presentation. Okay.
Just a second. Okay, can you see the slides?
Yes.
Okay, perfect. Okay, after Andreas talked about scientific reasoning competencies and their importance for science education, I will continue with presenting a learning sequence we designed in order to foster these competencies in an undergraduate lab course. And in this designing of the learning sequence, we had 3 aspects we put a special emphasis on. The first one is that for us, it was important that it is easily implementable. And for this purpose, we decided not to reinvent the wheel, but to build on experiments that are already there and that are already used in introductory lab courses. The second point is that we wanted to consider what science education research suggests concerning fostering scientific reasoning competencies. And there are already a lot of measures out there that have proven to be effective in fostering these competencies. The last but not least point is that scientific reasoning competencies are very complex constructs, and this complexity should be taken into account. And therefore, we decided not to design only one learning opportunity, but to design multiple learning opportunities that are sequenced coherently. This coherence can be achieved by aligning all learning opportunities to one common goal and to make sure that the learning opportunities build on each other. And this coherence in our case is achieved by sequencing the learning sequence in certain steps. First, the confrontation, in which the students are confronted with the first experimental problem and thereby might already identify knowledge and skill components that are relevant to solve this problem. This is the foundation for the step of acquisition, in which the students then have the opportunity to acquire these knowledge components that are necessary. These newly acquired knowledge components can then be applied in another experimental problem, and the application is reflected. In the end, we wanted to provide the students with another learning opportunity, with another experimental problem, which requires the students to transfer their knowledge and skill components, which they acquired before, to a new experimental problem. In order to design learning opportunities for each of these steps, we used 4 experiments from an introductory lab course at the Leibniz University in Hanover. And all 4 experiments are from the field of kinetics and allow to investigate the dependency of the reaction rate from different factors like the reactant's concentration, the catalysts, and the temperature. I don't want to go too much into detail here, but if you have questions concerning these experiments, we can come back to this later. These experiments were in a cookbook recipe style in the introductory lab course we took it from. So in order to design learning opportunities that allow to foster scientific reasoning competencies, we combined them with research-based measures. And science education research suggests that inquiry-based learning is suitable to foster scientific reasoning competencies, especially if it's combined with an appropriate degree of guidance. In our case, for undergraduate students, we assume that guided inquiry provides a suitable degree of guidance, which means that we provide the students with a research question, which they are asked to answer by conducting a scientific investigation. This was implemented by handing out pre-structured lab reports in which the students obtain a small introduction with information about the reaction they are going to investigate. Then the research question is stated, and then the phases of hypothesis generation planning and conducting an experiment, and data analysis and drawing conclusion is also included in this lab report, but left open for the students. We provided further guidance by providing a list of lab equipment and chemicals the students are allowed to use for their investigation. And we did this for two reasons. On the one hand side, this is a limited list, and therefore the material demand for the lab course is manageable. But on the other hand side, this list provides a certain degree of flexibility, so the students are able to vary and measure different variables, and therefore have to take into account the control of variables strategy. This way, we adapted the first experiment in order to design a learning opportunity for the step of the confrontation. And in this experiment, the students investigated the influence of the concentration on the reaction rate. For acquisition, science education research also has some suggestions. For example, Schwichow and his colleagues found in their meta-analysis that demonstrations and cognitive conflicts are particularly effective when it comes to introducing the control of variables strategy. Therefore, we designed a video task in which the second experiment was shown in a demonstration, but the way it was conducted was confounded. So the conclusions that were drawn were not valid, and the students were asked to evaluate the validity of the conclusions and to suggest improvements for the experimental design in order to have a valid investigation. Furthermore, science education research suggests to use explicit instruction to address underlying principles. And this was implemented in our learning sequence as well in a second video task in which the phases of experimentation and the corresponding criteria were addressed explicitly. Students then are provided with an opportunity to apply what they learned about the criteria of experimentation and the control of variable strategy. And this opportunity was implemented by adapting the third experiment, which investigates the amount of the catalyst, the influence of the amount of the catalyst on the reaction rate. The application was furthermore supported by including prompts in the pre-structured protocol. And these prompts asked the students explicitly to take into account what they learned about the quality criteria of experimentation. Another point that science education research often stresses is that in order to foster scientific reasoning competencies, the students should be provided with opportunities for explicit reflection. And this was also taken into account by a reflection task in which the student had the opportunity to reflect upon the validity of their own investigation that they conducted, and therefore could reflect on the extent to which they applied what they learned before. Last but not least, we designed another experimental problem by adapting the fourth experiment, which investigates the influence of the temperature on the reaction rate. And this experiment was again adapted in accordance with the principles of guided inquiry, and therefore required the students to transfer what they've learned and applied before to a new experimental problem. We just handed in a manuscript last week to the Journal of Chemical Education, where this learning sequence is described in more detail, and also in evaluation is described. And this is the last point I want to make here. It's about the evaluation. Of course, we were interested in the extent to which this learning sequence is suitable to foster scientific reasoning competencies. Therefore, we implemented this learning sequence at 2 different German universities, each time combined with an introductory lab course. And we had a total sample of 47 undergraduate students. And this learning sequence was evaluated empirically by coding the written lab reports of the first and the last experiment, which were thereby utilized as a pre and a post test. The coding was conducted based on a coding manual, and the categories of this manual were derived deductively based on prior research, and double coding of 23% of the material showed substantial inter-rater reliability. I can present first results from this coding. The coding manual allows us to produce a score for each phase of experimentation, and depending on how many criteria have to be taken into account in each phase, the score, or the maximum score, ranges between 4 and 13, depending on the phase. And coding showed us that for all phases, there are improvements from the first experiment, the pre-score, to the last experiment, which is the post score. And additionally, we conducted one-tailed t-test for paired samples in order to look for significant improvements from pre to post. As you can see, there are no significant improvement for the phase of generating a hypothesis, which actually is hardly surprising, taking into account that the pre-score of 3.74 is already pretty close to the maximum score of 4 for this phase. On the contrary, we found significant improvements for the phase of planning and carrying out an experiment, and for the phase of analyzing data and drawing conclusions, with high effect sizes, the Cohen's d of 1.01 and 0.92 respectively. So in conclusion, it can be said that, of course, there are some limitations. For example, we didn't have a control group. That's because of the design of the larger research project. But nevertheless, the successful implementation at 2 different German universities and the results of the empirical evaluation at least indicate that the learning sequence is suitable to foster scientific reasoning competencies in undergraduate lab courses. We have a lot of more interesting questions about scientific reasoning competencies and their development. And we are investigating them through the lens of the competency triad, which is a differentiated competency model. But I think the time is nearly over. So if you have any questions concerning this or anything else, just let me know. Don't hesitate to ask. But before I finish this presentation, I would like to thank first all the members of our research group for the pleasant and productive exchange. Of course, we would like to thank the organizers of this symposium for organizing it and for inviting us. And last but not least, I would like to thank you all for your attention during this talk. Thank you very much.